All right, folks, if I call this angle, let's just call it theta, okay? And let's say theta is 60 degrees. The discussions from earlier this week and late last week talk about how no matter what that angle measurement is, okay, in triangles that are similar to it, okay, so let's say every right triangle has a 60-degree angle in it. Every right triangle has a 60-degree angle is similar to every other right triangle that has a 60-degree angle, okay, meaning that its sides are proportional. If the triangle is a right triangle that has a 71-degree angle in it, then every other right triangle, no matter how big it is, that has a 71-degree angle in it, the sides are going to be proportional to one another. Okay? With 30, 60, 90 triangles, 45, 45, 90 triangles, the sides compare or relate to one another in very nice terms. Okay? With a 30, 60, 90, across from the smallest angle is always your smallest side, and we usually call that n. Okay? Across from the across from the right angle, which is the hypotenuse, is always twice that. So we call it 2n. And then the remaining side, which would be the middle length, is the smallest side times radical 3. So all three sides are written in reference to what the smallest side is. Okay? So if I ask you what is the cosine of 60 degrees, I'm asking you how that phrasing right there is asking you how does the adjacent side, because remember SOHCAHTOA, so I said cosine, so it says how does the adjacent side, which in this case would be n, compare to the hypotenuse, which would be 2n, right? Okay. Well, through a little bit of cancellation, doesn't that just give me 1 over 2? And what we're arguing there then is if we have a 60-degree angle, and I've messed all this up. Let me just open this up again. All right, so we're at a 60-degree angle, and we were doing cosine, right? So cosine is adjacent divided by hypotenuse. So I want to show CA and BA. All right, so what this is demonstrating is that as long as I've got this 60-degree angle here, being the angle that I'm referencing off of, no matter how big I make this triangle, whether I make it as big as possible or as small as possible, okay, so it fits on my desk, or it might take the tri-state area to contain the triangle. If I look at the 60-degree angle and compare the adjacent side by the hypotenuse, it's always going to be in a 1-to-2 relationship, okay, no matter what those lengths are. Does that make sense? And that's all because of similarity, okay? Now, the other side lengths are also in a particular relationship, okay? So there's the opposite of hypotenuse, so that's the sine. So sine is always in a 0.87 relationship, okay? It actually turns out to be radical 3 over 2 as an exact value, okay? And then the adjacent, oh, we already did that one. Opposite of adjacent, okay? That's radical 3, okay? But no matter what, those ratios should show up, okay? So what's nice about that is that when I have this here, okay, and in my triangle I was showing, let's see here, those two sides, there's a 1 to 2, or not those two sides, would the, there we go. Okay, there's a 1 to 2 relationship there, okay? And because we know there's a 1 to 2 relationship there, with no matter how big those sides are, the moment that I get rid of that side and ask you now, look at that figure right there, okay? And that's 28, and you got a 60-degree angle. Can you tell me what this side length is right here? And the reason you can tell me that that's 14 is because there is a scale factor of 1 to 2 here for those two sides. Does that make sense? And you can take 28, multiply by 1/2, and you get your 14 down here. Okay? But you can do that no matter how big that is. So 17.3, multiply by 1/2, give me the 8.65 that I need for down here. Does that make sense to everybody? Okay. So if cosine 60 is equal to 1/2, let me ask you this question. What is this angle right here? How big is angle C? 30. Okay. What trig ratio would, by referencing the 30 degrees, so now we're looking at that angle, which ratio would give me 1 over 2 as an output? Sine. If I go sine of 30, that's going to give me opposite over hypotenuse, so n over 2n, which then gives me 1 over 2, right? So because those are the same, what's that tell me about those two? They're the same, right? They're both 1/2. Okay, this is just another way of writing the number 1/2, right? Okay, this is another way of writing the number 1/2. What's the difference between, I don't want to say difference because you might, what's the relationship between 60 and 30? Okay, so give me a different relationship. I agree with that, but give me a different one. Okay, give me a different one than that. What's a geometric relationship that we know about those two angles? They add up to 90. And if two angles add up to 90, they're said to be what to one another? Complementary. Okay? So if you know one, you know the other one automatically, right? So if I say, cosine of, let's just say theta, that should equal the sine of 90 minus theta. Would you guys agree with that? Okay. Now, if that's the case, why does the word sine and the word cosine, why are they written that way? I'm not going to get into the, so I don't want to get into what's the word I'm looking for? The origin of this word sine. Okay? But if we establish that is opposite over hypotenuse, okay, then how does this relate to it? They both say sine in them, right? And the only thing that's different is this prefix at co. And what is that prefix at co telling me? Complementary. Okay? So that being said, if you know all your sines, so if you know sine of 28, you should automatically know then the cosine of 52, right? Does that make sense? Okay, let me use our calculator here real quick. And let's just, we use Desmos just to do it quickly. if you're going to use Desmos, so this all calculators are this way, okay? If you're going to be using degrees, you need to make sure you check the mode of your calculator, okay? So if you're a TI 384 person, okay, you need to click the mode button, and you'll come down here to the third or fourth line, and you see you can toggle back and forth between radian and degree. You need to make that decision on which one of those you're going to be in for every question. Is your question using degrees? Is it sine and then parenthesis and then a degree? Then you got to change your calculator into that mode. Is it sine and then like pi over 3 as the argument? Because that's radians. Then you need to change your calculator into radians. Does that make sense, everybody? Okay. If you're using one of these little calculators here, there's a DRG button. Degrees, radians, gradients. Okay. We only use degrees and radians here. So you'll push that button until you highlight degrees or radians in the bottom of your calculator. Okay. If you're using Desmos, you have to hit the wrench here and toggle back and forth. Okay. If you're a GeoGebra person, you actually have to use, so like I input like cosine of 30. Let's go to cosine of 60. Cosine of 60 should be 1/2. And if I hit enter, there it gives me 1/2. Okay? But there are times, just depending on how you've set up GeoGebra, that you might actually have to type in. See how it automatically put in that degree symbol for me right here? Okay? We were working in the last class. I had a different applet open from stats that I just kind of I deleted everything and brought back in. And the way I had that one set up was it was using radians. So when I typed in cosine of 60, it did not give me 1/2 back. It gave me some obscure number back because it thought 60 was in radians. Does that make sense? So the calculator that you use, you need to pay attention to what mode you're in. Okay? So when I'm in, I want to be in degrees right here in GeoGebra. So I'm going to say cosine of A and then sine of 90 minus A. And A is in degrees right now, so let's make this go between, so it's a right triangle, so A can only be between 0 and 90. Does that make sense? Anything outside that's going to make my triangle kind of dissolve or blow up. No matter where I stop this, are those two numbers always the same? So sine and the cosine are complement of one another. Does that make sense? Okay. Think about tangent. If I say tangent of A, okay, how can I get that 8.38 by using 90 minus A? What would be the complement of tangent? What trig ratio is similar to that relationship between sine and cosine, but matches with tangent? Tangent and cotangent. And we can see then that no matter what I put in for A, the tangent of A and the cotangent of 90 minus A, or the complement, are the exact same, right? What if I use secant? What matches up with secant in regards to the well, secant and cosine match up because of the reciprocals. But if I'm talking about the relationship now between adding to 90 or being complementary, cosecant, right? Does that make sense? Okay. And there we see that relationship. Okay. So the structure of our trigonometric ratio, sine, cosine, tangent, secant, cosecant, cotangent, those 6 things. Okay? Because some of them, 3 of them, are completely distinct words. Sine, tangent, and secant are complete distinct words, right? Cosine is essentially a derivative of one of those. We added the prefix co to it, right? Cosecant, derivative of one of those. Okay, I guess it kind of be antiderivative because it got bigger, okay, in regards to the length of the word. Okay. but they're related that way. Does that make sense to everybody? Okay. So there's 3 of those that have the word co on them, or the prefix co on them, and they relate to the other 3 by being equal in regards to complement angle. Okay. So that's a relationship that's going to be necessary for us to recognize and to be able to utilize here eventually. The one thing that is troublesome is that people, if I go with sine of theta, what is the reciprocal? So the reciprocal of that is 1 over sine of theta, right? Does that make sense? Okay, so I don't want to write it. Sine of theta equals 1 over sine. So those are reciprocals. Okay, because if I multiply those, I get 1, right? And that's the definition of a reciprocal. They're multiplicative inverses, and their product gives us 1. This gets kind of nasty. There will be times where we like to use this, times where we don't like to use this. Okay, we redefine it as cosecant. So sine and cosecant do match up to one another, or do relate to one another at some point, but it's in regards to being reciprocals. Does that make sense? Okay. Sine and cosecant are reciprocals. What about cosine? The cosine of theta, its reciprocal is 1 over cosine, which is equal to secant. Does that make sense? Okay. What if I write 1 over secant? What's that the same as? It's cosine. Okay. So these are two-way streets. 1 over secant is equal to cosine. 1 over cosine is equal to secant. Okay. Those are relationships that we need to be able to recognize and be able to understand. Okay. One thing that I found in trig is that what makes it so much easier is if you understand these underlying relationships. Okay. It's kind of like going back to 2nd grade, 3rd grade. Okay. Is multiplication pretty hard if you can't add? Yep. Okay. And you might not have realized this when you were doing division, but division is just repetitive subtraction. Division is pretty hard to do if you can't add, subtract, or multiply. Okay. This class, trig, I know we're only in the 2nd week, it's going to be very difficult if we can't grasp these fundamental foundational concepts. Okay. Because they're what everything else is built upon. All right. One of those things being special right triangles. Special right triangles are kind of the driving force of a lot of things that we do in the class. So if you're a person that struggles with these in geometry, okay, my hope is that you now take the time to kind of justify these, make sure these make sense to you, make sure you understand how the sides relate to one another, okay, where these parts go in every 30-69 triangle, because without that knowledge, things are going to get very, very frustrating for you. Questions so far on this? If we're to ask us, what is the sine, cosine, or tangent of ultimately a multiple of those two numbers, 30 or 45, we should be able to express our answers as an exact value. We should be able to say that it's 1/2, radical 3 over 2, radical 3 over 3, radical 3, those types of things. Okay? Those types of exact values. And that's because of special right triangles. Okay? Even if they ask you, what's the sine of 210, eventually, and this is the goal for the next couple of weeks, if they say sine of 210, my hope is that 210 is how many degrees bigger than 180? 30 degrees. Okay, so that right there tells me I got a 30. When I talk about 210, I'm talking about 30, 60, 90 triangle. Okay, so when I talk about 30, 60, 90 triangle, 210, 30 degrees. So sine of 30 degrees is 1/2, right? So sine of 210 has to be 1/2. Okay, but there's a component to that we need to pay attention to, and it's going to be that it's in the 3rd quadrant, and all your values in the 3rd quadrant are negative. So sine of 210, let's see if it gives us negative 1/2. So I need to go into degree. And I'll type in sine of 210. And you see that it gives us negative 1/2 back. Okay? So that's the goal eventually. Now, obviously, you have maybe no idea how we did that. But you'll be able, when I say, sine of 240, you'll be able to rattle that off right away based on what you know about 3069 triangles. But if you don't know anything about 3069 triangles, it's going to be very painstakingly difficult for you to find that negative 1/2. Okay? So we should, when we talk about this table, it only goes 30, 45, 60. Okay, but it should be, we can extend this to all multiples of 30 and all multiples of 45, all the way up to 360 degrees. Okay? And we can adjust then the positive and negative values here. If they do not give me a multiple of 30, 60, or 90, right now, what we will have to do is use our calculator. So if they say tangent of 40, then I got to know that they're talking about degrees. Make sure my mode is in degrees. And then just type in tangent of 40. 0.839. So what that tells me then is that every single right triangle, it only works for right triangles. Okay, so SOHCAHTOA is just for right triangles. If we have non-right triangles, then we start using laws of sines and laws of cosine. Okay? But 40 degrees, right triangle, I now know that every triangle that is right and has a 40-degree angle, the side opposite of the 40 divided by the side adjacent to the 40, always divide in a 0.839 manner. Okay? That's how it's always compared. That kind of makes sense what that number is? I think when we were in geometry, I tried to explain this in geometry, but remember that was 2 years ago, and some of us maybe weren't as mature as we are now. So we went through that, we talked about it, but I think from that, just from my experience working with geometry students, is that became more of a procedural approach to geometry. We just basically said, okay, if I'm looking for this distance, then I use this ratio, plug it in, do the algebra, type my calculator, and let it spit a number out. Okay? We didn't really spend a whole lot of time. I tried to, but we didn't spend a whole lot of delving into what this number represents. This number is a representation of the ratio of an opposite side divided by adjacent side for a 40-degree angle. Okay? And that's always going to be the case, no matter how big the triangle is. If it fits on a piece of paper, or if it takes the galaxy, it's going to be 0.839, the way we understand it. Does that make sense? There's a lot of other ones here that I don't necessarily want to do. Cotangent of 14, though, just most of your handheld calculators. Can you find the cotangent button on your calculator? You can't, because there isn't one. Okay, TI does not make a, Casio might have one, but your TI does not have a cotangent button. So if I want to use cotangent, I have to know what is cotangent's reciprocal. Tangent. So cotangent and tangent are reciprocals, right? So if I want the cotangent of 14 degrees, I actually got to write 1 divided by tangent of 14 degrees. Does that make sense? Okay. Now, what I like about Desmos is that I can type in cotangent of 14 degrees. Okay. So that's nice, but that also circumvents me needing to know or attaining the knowledge that cotangent and tangent are reciprocals. So there's kind of a cost and reward to what technology you use to evaluate that. GeoGebra also allows you to type in cotangent as well. All right, so let's get into, these are geometry questions, 9th grade, 10th grade geometry, but we'll start with these. Basically when it says solve the triangle, what that's asking you to do is find all the missing parts. So there's 6 total parts to a triangle. They're usually going to give you 3 of them or 2 of them. And you got to find the other 3 or 4.
Big C is 90 degrees.
Okay, so yeah, big C is 90 degrees. The one thing we need to pay attention to is that when we look at 90 degrees, we will never ask what the sine of 90 is, what the cosine of 90 is, what the tangent of 90 is, based on a right triangle. Okay? We will ask those questions. We will ask, you know, sine of 90, why is that 1? Cosine of 90, why is that 0? Tangent of 90, why is that undefined? We'll ask those questions and analyze those eventually. But inside a triangle, I'll never ask you, what is the opposite side divided by the adjacent side to the 90-degree angle? Because this would be the opposite, and then both these would be the adjacent, right? And then you don't know which one to choose for the adjacent. Okay, so there's ambiguity there, so we don't ask that question. But if I look at this 30 degrees, and I want to find A and B, what is A in regards to this 30? The opposite. Okay, so let's say that I'm going to write which trig ratio uses opposite. And I have to use this number here, right? Does that make sense to everybody? Okay, I can't use opposite and adjacent because that would be 2 unknowns in my equation. So I got to use opposite and hypotenuse. So I'll say sine of 30 is equal to opposite over hypotenuse. Now what will you do to solve for A? Multiply by 12. Okay, now when I type in sine 30 on my calculator, what's sine of 30? 1/2. So that's going to give me A to be 6, right? And that's one approach that you can use in these types of problems. Okay, let's go ahead and find B real quick before we talk about a second approach. If I want to find B, that's the adjacent. And now that I have A, I could use A as well. Does that make sense? Okay, so I could do that. The caution that I would want to remind you of, I guess, is if this number A had to be rounded at all, don't use it. Okay? Because if I use rounded values, that's going to get compounded in my next calculation, right? Okay, so I want to avoid compound error. So let's go ahead and use adjacent and hypotenuse. So which trig ratio uses adjacent and hypotenuse? Cosine. So I have cosine of 30 is equal to adjacent. So B over 12. So 12 cosine 30. Okay. Now I type in 12 cosine of 30. $10.39. That's my length for B. Okay? And that's perfectly fine right now. Okay? Because I didn't set out any instructions on how I wanted your answers to be provided. Okay? However, a rule of thumb is if they use a multiple of 30 or a multiple of 45, they are going to want your answers to be exact. And this 10.39 is not exact. If this is a 30, 60, 90 triangle, don't we know that the opposite side should be in? The hypotenuse should be 2n. And the side that is in the middle should be in radical 3. And now, okay, now if I know that 2n is 12, right? Does that make sense? Okay, so basically when I write this template on top of, I get 3 equations. I get A equals n, I get B equals n radical 3, and I get 2n equals 12. Only one of those will ever be able to be solved. Okay? 2 of them have 2 variables in them, right? But 2n equals 12 has 1 variable, so what's n got to be? 6, and n was A, which is what we got there, right? But now here we're seeing that B is 6 radical 3. And if you were to type in 6 radical 3 on your calculator, it gives you that 10.39 number. But which one's better? 6 radical 3. There's absolutely 0 rounding in 6 radical 3. And the reason we want that is because eventually that 10.39 number is going to be used as an intermediate value for another calculation. And if we use 10.39 and it's rounded, that rounded error is going to be kind of re-emphasized and probably made greater as we use it inside other calculations. But 6 radical 3, no error. Okay? Does that make sense? And the nice thing is, like, you just think about this. Because people always argue, well, 10.39 makes so much more sense to me. It's easier. It's easier for me to do that. I'd agree with that. But if I ask you to take 10.39 and I ask you to square it, take a moment and do that. By hand, multiply, no calculator. 10.39. That's hard, right? But if I ask you to do 6 radical 3 squared, isn't that 36 times 3? That's easier, isn't it? 108. Okay. So there you get maybe the necessity, or you prove a necessity, or the reason, I guess, why maybe leaving things as exact values and radicals might be easier, okay, in the long run. All right, so this next question, I think it's the last one we'll do. Yeah, this is as far as we got in last class. So, power of 6. What kind of unit is that? It's a radian, okay? Unless it has the degree symbol, it's always going to be radians, okay? It doesn't, the pi is a good giveaway that it's radians, okay? But pi divided by 6, that's going to be irrational, so I'll have to round a little bit, is 0.52. So if they would have just put 0.52 in there, I have to know that that's still radians. Does that make sense? There's no degree symbol. So if there's no degree symbol, it is radians. So pi over 6. Talking about radians here. So all that means to me is that when I grab my calculator, I change that to radians instead of degrees. What side would this right here be? Let's just call this A. What side would A be in regards to that pi over 6? It's the opposite. Okay. So what side would B be down here? It is the hypotenuse. I would agree that it's adjacent. But that one is adjacent, and so is that one. Whenever you look at the adjacent side of a acute angle of a right triangle, one of them is going to be the hypotenuse. And that being the hypotenuse supersedes being adjacent. So we're going to call that hypotenuse. And then 72.3 is the adjacent. All right, so let's go ahead and find A. So if I'm going to find A, I've obviously got to use A in my formula, right? And what other segment do I have to use? Adjacent. So I use opposite and adjacent. So which trig ratio does that elicit? Tangent. So it's tangent of pi over 6 is equal to opposite over adjacent. So 72.3 tangent of pi over 6 is equal to A. We'll grab our calculator. Change your mode, because we're in radians. Last class I told you, you might have 10 questions. 5 of those questions will probably be in degrees. 5 of those questions will be in radians, and they'll bounce back and forth every other. Okay, you might see assignments like that. So you might have to change every single time that you do a problem. Does that make sense? So 72.3 tangent of pi over 6. Gives me that number right there. Okay. Now here's my hope for us eventually. Do you remember what pi over 6 is as degrees? 30. So what if I went back to mode, changed it to degrees, typed in 72.3 tangent of 30. Give me the same number? Okay. Does anybody know in a 30, 60, 90 degree triangle, across from 30 is the inside, right? And the adjacent to that would be the n radical 3. If I divide those, don't I get radical 3 over 3? So tangent of 30 is radical 3 over 3. That's the exact value. Come back up here to this chart. 30, tangent of 30 radical 3 over 3. So instead of typing in 72.3 times tangent of 30, I could have typed in 72.3 times radical 3 over 3. Same value. Does that kind of make sense? And those connections are what my hope is for us to be able to recognize and learn and use as we navigate through the course. Okay? But nonetheless, we get, what do we say, 41.74? 41.74. Now, as I go try to find B, would I want to focus on using that number? No, it's rounded, right? Okay. Could I use that number? Yeah, that one's not rounded, right? So we could do a couple different things here. Let's just go ahead and find B without using the 41.74. Let's not use that. So I got adjacent and hypotenuse. So adjacent and hypotenuse would use what? Cosine. So I'm going to go cosine of pi over 6 is equal to adjacent. So 72.3 divided by hypotenuse, which is B, right? You guys remember what happens when you have your variable in the denominator on a sine, cosine, tangent equation? Yeah, I'm gonna multiply both sides by B to get that fraction to go away. And then to isolate B, I'm gonna divide by cosine of pi over 6, right? So the shortcut is that the left-hand side and the denominator just switch spots. And we can then get B. So then we got 72.3 divided by cosine pi over 6. And I know I changed my mode previously. So I go back to radians. And I get that distance there. Does that distance make sense compared to this one right here? What's the relationship between those two numbers? They're double. Because it's a 30, 60, 90 triangle, right? This one's the hypotenuse. This is the smallest side. Okay. If we wanted to use A to find B, opposite, I would use sine, right? So let's say sine of pi over 6 is equal to A, 41.74. But I don't want to round it. So I'm just going to type in 72.3 tangent of pi over 6. That's what A was, right? Can I divide that then by B? I can write it that way. And that will turn out to give you the exact same thing as 72.3 divided by cosine pi over 6. And the whole, I don't want to say the whole purpose, but a portion of this class will be able to realize, okay, well, why is tangent of pi over 6 sine of pi over 6? Why are those still, because essentially those two parts are what's different over here, right? The sine of, or sorry, the tangent of pi over 6 divided by sine of pi over 6 over here is just the cosine of pi over 6 in the denominator, right? So let's talk about that real quick. So I think we talked about this in, before I left. Tangent is the same thing as what? Tangent theta, you guys remember what that's the division of? Because remember it's sine divided by cosine? Okay. Would you guys agree then that this thing here would be 72.3 tangent? I can rewrite as sine of pi over 6 divided by cosine of pi over 6. You guys agree with that? Divided by sine of pi over 6 then, right? How do I divide a fraction by a fraction? Multiply by, is that the reciprocal right there? Or that's the denominator, right? I'm going to take that reciprocal, which would be 1 over sine of pi over 6, right? What happens to that sine of pi over 6 in that one? Cancel this one away. I have 72.3 times 1. And then on the bottom, I just got cosine pi over 6, right? Is that The exact same thing that we had right there. Okay. So my hope is what we realize here is we have alternate approaches, and if we are good with our algebra and we know these relationships between different trig ratios, we should be able to essentially prove two different answers are identical, or two different formats are identical. At the beginning, we kind of talked about complement angles real quick. Let's kind of make a transition back to college algebra. If I have sine of x, okay, and I know those of you in physics you're gonna talk about this eventually. Sound waves, light waves, electromagnetic waves, they travel this way. Okay, and we understand them this way. Okay, sound waves are compression waves, and they travel a little bit differently, but we can analyze them like a sine wave like this. This is the cosine wave. Okay, and this is all based off of what we just talked about with the right triangles. Okay. What does it look like I could do with this red one to make it that green one? I could shift it, right? Let's take cosine of x. Now, how do cosine and sine relate to each other? They were what to one another? Sine, cosine. They're complement, right? They're we call that cofunctions. Well, if I go 90 minus x, cosine 90 minus x, actually I want 90x. Let's do it this way. So I want the, delete. All right, so I want this one to become that one. Does that make sense? Okay, this one to become that one. So I'm going to take the sine, and I'm going to move it to the right. So go sine. Okay, moving to the right will be subtraction, right? Now, when I go 90, it doesn't move it the way I want it to. I'm going to go pi over 2. What happened here? Got it backwards. Sorry. I wanted to... It's pi over... Sorry. Pi over 2 minus... There we go.
There you go.
So, we'll talk about this tomorrow. We'll start here with tomorrow. Have a good one.